This is a challenging ALEX problem that requires multiple steps to answer. It says a chemist titrates 160 milliliters of a 0.2643 molar benzoic acid solution with 0.7066 molar KOH solution at 25 degrees C. Calculate the pH at equivalence, and it gives us the pKa of benzoic acid. So equivalence is when the moles of benzoic acid and the moles of KOH are equal. And at that point, what we're basically going to have is a potassium benzoate solution with a certain molarity, and then based on the pKa, or the Ka, we can determine the pH of the solution. So this is a multi-step thing. So the first thing that we want to consider is the reaction of benzoic acid with KOH. So the reaction is HC6H5CO2 aqueous plus KOH aqueous yields, H goes with OH to form water, and K goes with benzoate, so we get KC6H5CO2 aqueous plus H2O liquid. So this is our reaction. So at equivalence, the moles of this and the moles of this are equal, which essentially means we have a solution of this. A solution of this, which is a weak base, a relatively weak base, is a weak acid, so it's certainly a base. Let's just put it that way. And this base is going to be in solution. But in order to determine the pH of the solution, we need to know the concentration of this base. The problem is we know how much acid we used, but we don't know how much base we use. So the first thing we need to do is a stoichiometry problem just to figure out how many liters of or milliliters of KOH were used, so we know the total volume of solution, so we can determine the concentration of this in the equilibrium solution. So let's start by doing that. So the first thing we want to do is to go from liters of benzoic acid, which I'm going to abbreviate BA, to moles of benzoic acid, to moles of KOH, potassium hydroxide, and then finally to liters of KOH solution. So in this case, we started with 0.1600 liters of benzoic acid solution. No, I just took the milliliters and divided by 1,000 times. We're going to use the molarity to convert this to moles. We know there's 0.2643 moles of benzoic acid per liter. So we put 1 liter of benzoic acid solution on the bottom and the 0.2643 moles of benzoic acid on the top. Times. We have a 1-to-1 stoichiometry. So there's 1 mole of benzoic acid per 1 mole of KOH. Then finally, we want to find liters of KOH. So this time we put the 1 liter on the top, and the KOH solution is 0.0766 molar. So we put the 0.7066 moles of KOH on the bottom, and on top we put the 1 liter of KOH. And when you do that, we find that it is 0.05984,716 liters, and that's the sig fig, or 59.84, and I'm going to keep the 716 milliliters. So I just multiplied that by 1,000. So this is how many milliliters of this base we added. Remember, we need to know this volume because we need to find the total volume of solution so we can find the concentration of this. This is 1-to-1 with the acid, so the conjugate base is 1-to-1 with the acid. The goal is to find the concentration of the conjugate base in the final solution. So our goal is to find the concentration of C6H5CO2 minus, or K C6H5CO2. This is just the counter ion. So this is our goal, is to find this. Well, we know the initial concentration of the benzoic acid is this, and we know the initial volume is this. So that would also be the initial amount of this. So what we're going to do is take the 0.2643 molar, C1V1 equals C2V2, times the initial volume, 160.0 milliliters, equals C2, the final concentration, times the total volume, the 160 milliliters of the original benzoic acid that was added, plus the 59.84 milliliters of the base that was added, which is a total of 219.84716, where that's the sig fig. So I just added the volume of KOH and the volume of the original acid. And when you do that, you find that the concentration of this acetate ion is equal to 0.1923518 molar, where that's the sig fig. So we now have the concentration of acetate in solution after the titration has been completed and we've reached the equivalence point. We now have a question very similar to a few questions ago on this playlist, where we have a weak base in solution. So let's take a look at this. So all of that was just to find the concentration of the weak base in solution. So now we have this base, C6, the conjugate base of a weak acid, C6H5CO2 minus aqueous, plus water, liquid, and it's going to be in equilibrium, where it's going to take a proton away from water, and we're going to get HC6H5CO2 aqueous plus OH minus aqueous, like this. And we know a few of these things. We know the initial, the change, and the equilibrium concentrations of some of these things. The initial concentration of this, we spent all that time figuring out, 0.1923518. Water we don't care about. The initial concentration of the acid is 0, and the initial concentration of the hydroxide is 0. Now we're going to look at the change in the concentration. So in this case, we're going to subtract x of this, and we're going to add x of each of these. So at the end of the day, we're going to have 0.1923518 minus x, x, and x. Well, now we can use our Kb expression. The Kb is equal to the concentration of HC6H5CO2, the first product, times the concentration of OH minus, the second product, divided by the concentration of C6H5CO2 minus, the reactant, and we ignore water because it's a liquid. Now we're not given the pKb, we're given the pKa. And in order to find that, the first thing we want to do is take that the pKb equals 14 minus the pKa. So the pKb equals 14 minus 4.20, and the pKb equals 9.80. Then we want to find the Kb. Well, the Kb is 10 to the negative pKb. So the Kb equals 1.58 times 10 to the minus 10. So we can find the pKb by taking 10 to the negative 9.80, and we get 1.58 times 10 to the minus 10. We now have the Kb. we're going to assume here that X is very small as compared to the concentration of this, which in all the examples I saw was a valid assumption. So now we're going to plug into this equation. 1.58 times 10 to the minus 10 equals X times X over 0.1923518. And again, oops, that's the sig fig. And again, we're going to just pretend that the X doesn't exist. Cross multiply, multiply X times X, and what you get is X squared equals 3.0486 times 10 to the minus 11. And I believe the sig figs fall apart a little bit here, so I'm going to go ahead and ignore them. And what you find when you take the square root of both sides is that X equals 5.52 times 10 to the minus 6. This is the concentration of OH minus. So now we have the concentration of OH minus. Well, if we have the concentration of OH minus as X, I'm going to kind of make myself a little space here because this is such a long problem, I'm running out of space. What we can do is we can find the POH. The POH equals the negative log of the concentration of OH minus. The concentration of OH minus is X. So the POH equals the negative log of the 5.52 times 10 to the minus 6. Or the POH equals 5.25. Whoops, 5.25. But at the end of the day, we're asked for the pH of the solution. Well, the pH and the POH equals 14. So the pH equals 14 minus the POH. So the pH equals 14 minus 5.25, and the pH equals 8.74. It might equal 8.75 here. I think I forgot a few sig figs here. This is probably not exactly 5.25. So 8.74 or 8.75, it's only off by 1 in the hundredths place. So this particular example is quite complex. To very briefly review what we did, the first thing was we used the stoichiometry to figure out the volume of KOH that we needed. We realized that at the equivalence point, we essentially had a solution of this. We then used C1V1 equals C2V2 to find the concentration of the conjugate base in the final solution, which was this. We then realized that this conjugate is the conjugate base of a weak acid, and we used the icebox to determine basically the Kb, and we found each of the values. We assumed that X was small compared to the size of this, and if you look at it, X is very small compared to the size of this. It's much less than 5%. So we ignored it. We then plugged into the Kb expression, X times X, over the concentration of the benzoate equals the Kb. We found the value of X, which is the concentration of OH minus. We then use the concentration of OH minus, this one, to find the POH, because POH equals the negative log of concentration of OH minus. We found the POH. Then the pH equals 14 minus the POH, so we took 14 minus the 5.25, and we got a pH of 8.75 probably, but I have it as 8.74 here, which I believe is the answer on the answer key. I don't think Alex will give you the wrong answer if you're off by only 1 in the hundredths place. So this is a very involved problem that takes quite a bit of practice.